Hello everyone, this is Professor Roman. Let's continue the field theory lectures. In the last lecture we began an overview look at Galois theory. We talked about algebraic formulas, the general algebraic formula for the general polynomial, and we talked about the class of field extensions that are expressible by formula, and we proved that that class is strongly distinguished. Today I want to talk about another class of extensions that are strongly related to the extensions that are expressible by formula. In fact, in the finite case, they are equivalent. So let's begin with some definitions. A proper field extension Fe is an nth root extension for n bigger than or equal to 2, or has type n, if E is F with alpha adjoined, so alpha is generator for E over F, and the alpha to the n belongs to the base field. And we'll also say that alpha is a type n witness for this extension Fe. So to say it's a type n witness is to say it generates E over F and its nth power falls into the base field F. When we don't care to mention the type, we'll just refer to Fe as a root extension. A tower of extensions where the kth step, rk minus 1 to rk, is either trivial or is an nth root extension, an nkth root extension I should say, is called a radical tower. And the extension is called a radical extension. So notice this is n sub k, which means that the type can vary among the steps in the tower. You could have a type 2 extension, you could have a type 5 extension, and so on. They're not related. A radical tower can also be written in this form, where we are adjoining an element, single element at each step. And if the step is non-trivial, then the element alpha sub k that we adjoin is a type nk witness for that step. I'm going to refer to the types n1 through nm of the steps as the step types for the tower. And finally, I'll denote the class of all radical extensions by script r. Allowing trivial steps in a radical tower is not a big deal. It's just a matter of convenience, as we'll see as we continue. Sometimes when we manipulate a radical tower by lifting or intersecting with another field or something, we might reduce a non-trivial step to a trivial step. And I don't want to have to keep saying, well, let's take out any trivial steps. So we won't worry about trivial steps. Let's look at the properties of radical extensions. They also have some nice properties, as does the class of extensions that are expressible by formula, but not quite as nice. There's one sort of glitch here. So let, again, script R be the class of radical extensions. As far as lifting is concerned, the root extensions are closed under lifting and preserve type. And you'll see what I mean by that in a second. Therefore, R is closed under lifting. And this too will require explanation. Concatenation, if we have a two-tower, and if the lower step and the upper step are radical, then the full extension is radical. Composite, if FR and FS are radical, then so is FRS. Normal closure. This is going to be an important one. If FR is a radical extension, so is F normal closure of R over F. Well, as for proof, for part 1, if we have an nth root extension with witness alpha, and if K is an extension of F, then when we lift this extension using this, we get K with alpha joined. Well, that could be trivial if alpha happened to be in K. But if it's not trivial, it is an nth root extension with the same witness alpha. Because after all, alpha generates this extension over K, and alpha to the n is in F and therefore in K. Now, suppose that, again, we have an extension K of F and that we have a radical tower. We want to be a little careful here about how we do the lifting. Here is an arbitrary step, Rk minus 1 Rk. Rk is Rk minus 1 with the witness adjoined. And if we lift this by K Rk minus 1, the lifting field has to contain the base of this step, and it does. K Rk minus 1 contains Rk minus 1, so we can lift. And on the lower end, we have the composite of K Rk minus 1 with Rk minus 1, which is K Rk minus 1. And on the upper end, we lift by this, we're lifting this, so we have K Rk minus 1 with alpha K adjoined. And the latter here, Rk minus 1 with alpha K adjoined, is Rk. So now we have K Rk minus 1 to K Rk. And that is either trivial if K has enough stuff in it to kind of absorb the step here, or it's a root extension of type Nk. As we have the same discussion we had before. Alpha K generates KRK over KRK minus 1, and its nth power lies in F, and so it lies in here. So this tower, where we have taken the composite of each of these with K, is also a radical tower. And so KR is a radical extension. That's the lifting of FR by K. So we are, just to note, we are lifting by different amounts for each step. For part 2, this is concatenation. If we have two radical towers, one going from F to R, the other going from R to S, then all we have to do is concatenate them, and we'll get a radical tower from F to S, and so Fs is a radical extension. Part 3 is composite. I have to work a bit harder here. I'm sorry, part 3 is composite. That's easy because it follows from concatenation and lifting. It's part 4 that we have to work a little harder at, and that's the normal closure. There was a theorem back in chapter 2 that told us that the normal closure of R over F is the join of the images of R under the embeddings over F of R into, say, R bar, a fixed R bar. Now, since FR is a finite extension, this set is a finite set, and I'll let you ponder that. Therefore, the composite here is a finite one. Now, if we have a radical tower, and again we have our witnesses, so I wrote it this time to say alpha k to the nk is in the base field rk, and if sigma is an embedding of R into R bar over F, then sigma rk plus 1 is sigma rk with alpha k adjoined, and that is sigma rk adjoined sigma alpha k. And sigma alpha k raised to the nk power is sigma of alpha k raised to the nk, which belongs to sigma of rk. And so this tower is also radical. So F sigma R is a radical extension, and therefore so is a finite composite of things that look like that. In other words, so is F normal closure of R over F. One shouldn't get the impression that all finite extensions are radical extensions. And here is the case in point. A normal extension of the rationals, QE, that has prime degree P, bigger than 2, cannot be a radical extension. So suppose, to the contrary, that it is a radical extension. This has prime degree, so there can only be one non-trivial step in a radical tower because of the multiplicativity of degree. So in fact, QE itself is the only radical tower, and that means that E must be Q with an element adjoined, and some power of that element must fall into Q. In other words, alpha to the P is in Q. And in fact, the minimal polynomial for alpha over Q is x to the P minus alpha to the P. But because we're assuming QE is normal, all the roots of this minimal polynomial have to lie in Q with alpha adjoined. But this complex number is one such root, e to the 2 pi I over p alpha. And so if this root is in fact in Q with alpha joined, then so is this complex number, e to the 2 pi I over p. But if you look at this tower, there's a big problem. The full degree is p, but the lower step has degree p minus 1. That's something we proved in the ring theory course. Basically, it amounts to the fact that this polynomial is irreducible over the rationals. Well, p minus 1 doesn't divide p. So there's a contradiction here, and the extension cannot be radical. It cannot be a radical tower. It cannot be a root extension. as a corollary to the previous theorem, the roots of this particular rational polynomial are expressible by formula over the complex numbers, for example. And so if S is a splitting field for P of X over Q, then QS is expressible by formula. But it is not a radical extension. Why is QS expressible by formula? Well, the cubic formula, Cardano's formula, which we'll discuss later in the book, for the roots of a cubic equation shows that the roots of P of X are expressible by formula, and therefore they generate the splitting field, and so QS is expressible by formula. Now, we're going to prove later in the chapter that this extension has degree 3. It could conceivably have degree 6, but it doesn't. And so the previous theorem applies, showing that this extension is expressible by formula, but not radical. So that's ironclad evidence that those two classes of field extensions are not the same. Well, then, what exactly is the relationship between the class of extensions that are expressible by formula and the class of radical extensions? Every radical extension is expressible by formula. And to see that, all we need to do is show that any step in a radical tower, any root extension, is expressible by formula. Well, the generator is an nth root of something you already know about, so that's one of the 5. Taking the root is one of the 5 basic algebraic operations. So there's a one-step construction for alpha, because alpha to the n is in F. So the construction is simply to take the nth root of alpha to the n. One-step construction sequence to get alpha, and so alpha is expressible by formula over F, almost trivially. Not quite, there is one step. And so this extension is expressible by formula. So every individual step in a radical tower is expressible by formula. And since the class of extensions that are expressible by formula has the tower property, it's strongly distinguished, the full extension is expressible by formula. As far as a partial converse, we can't hope for a complete converse because these two classes aren't the same. If F alpha joined is expressible by formula, and I have over F here, and again, I don't need that. I seem to make the same mistake consistently. Then a construction sequence for alpha produces a sequence of field extensions. Each time we add another element to the construction sequence, we can adjoin it to the previous field and get this tower. Now, if a particular alpha k, is formed from the elements of the previous field using only the 4 basic arithmetic operations, then that step going from here to here is trivial. If alpha k is the sum of alpha 1 and alpha 2, you haven't increased the field size any. It's the same field. So we can remove any of these trivial steps and re-index, and assume then that every step here is the taking of some root. It's not the application of the arithmetic operations. The only thing left is taking a root. In other words, each step is a root extension, although it still may be trivial. If you have, let's say, 4 is an element of one of these fields and you want to adjoin its square root, well, you're adjoining 2. And so let's say f is the rationals. So you haven't done anything. So some root extension are actually trivial. But that's okay. We don't care about that. The point is, every one of these steps is a root extension. And so f to e here, e being this last one, is a radical extension. And it contains e. Okay, so did I say it's contained in E? F with alpha adjoined is contained in E. F E is a radical extension. Alpha is contained in E, so F with alpha adjoined is contained in E. It's very early in the morning here, so I'm still not fully awake, I guess. Now, more generally, if we have a finite extension that's expressible by formula, we can always write E as F with some generators adjoined. Now, F to F with alpha 1 adjoined is expressible by formula, and so by this argument, there's a radical extension, F R1, that contains F with alpha 1 adjoined. F with alpha 2 is expressible by formula over F, and therefore also over R1. So there's a radical extension, R1 to R2, that contains F with alpha 1 and alpha 2 adjoined. And if this radical extension contains F with alpha 1, alpha 2 adjoined, so does this one. Okay. Well, we can continue with this until we finally arrive at a radical extension FR that contains E. I probably shouldn't have used E here in these two paragraphs because they're different E's, but that was bad judgment on my part. Anyway, so what we have learned is that radical extensions are expressible by formula. Finite extensions that are expressible by formula are contained in radical extensions. You can't hope for anything more. There are infinite extensions that are expressible by formula. I'll let you think on that. But radical extensions are always finite. So there are many ways to see that the converse isn't going to work here. So this is what we have. A finite extension is expressible by formula if and only if it is contained in a radical extension. And that is quite enough. Definition, standard definition. A field extension Fs is solvable by radicals if it's contained in a radical extension. A polynomial, p of x, or the corresponding equation, p of x equals 0, is solvable by radicals in f bar if its splitting field is solvable by radicals, and so contained in a radical extension. So we can translate the theorem I just quoted to you as follows. A finite extension is expressible by formula if and only if it is solvable by radicals. So the class of extensions that are solvable by radicals is strongly distinguished because the class of finite extensions that are expressible by formula is strongly distinguished. Actually, you have to be careful there because finite extensions aren't closed under arbitrary composites. So the class of solvable by radicals extensions is distinguished. So this theorem relates two different perspectives on the issue really that our ultimate goal here. Expressibility by formula for the splitting field S of a polynomial P of x tells us that there's an algebraic formula for the roots of the polynomial. That's kind of what we're after. Well, in the negative sense, we're trying to show there are no formulas in general. But solvability by radicals expresses the idea that a splitting field, S, can be decomposed into a radical tower. So on the one hand, we have expressibility by formula, which is what a search for which has been going on for 4,000 years. On the other hand, we have this notion of radical tower extensions or radical extensions. Extensions, fields that are reachable using the 5 basic algebraic operations. So I think that the notion of expressibility by formula appears less mathematically tractable than the notion of solvability by radicals. There is considerably distinct feeling between the two classes of extensions. The idea of expressibility by formula is quite old and often a little vague, although I've tried to make it precise by the definitions I gave in the last lecture. But there's something, I think, a little more tractable about the notion of a radical tower. I guess that's just an opinion. The essence of Galois theory is to take advantage of this difference in tractability, specifically by showing that the splitting field cannot be contained, of a polynomial, obviously, cannot be contained in a radical tower. We learn instantly that the splitting field is not expressible by formula. And so we can't get the roots of that polynomial by formula. And if that's the case, then there's no general algebraic formula for the roots of all polynomials of that degree, the same as the degree of P of x. So that is how we crack this issue. People will often say to me, students will often say, how could you possibly show there can't be an algebraic formula like the quadratic formula for fifth degree equations? And it does seem like that's maybe an impossible task at first thought, But the fact is, this is the route to showing that. By showing that there is an individual polynomial whose roots don't have algebraic formulas, we crack the whole thing wide open. There can't be a general formula for all polynomials if there's no specific formula for a specific given polynomial. Well, to illustrate the proof that no general formula exists of degree 5, the theory that we're going to develop in the rest of this course will show, through the use of the theorem we just discussed, that the roots of this quintic, and this is just an example, this quintic polynomial are not expressible by formula over the rationals. So there's no general formula of degree 5 over the rationals. And to give you a clue as to why the roots of this polynomial are not expressible by formula, let S be the splitting field that lies, say, in the field of algebraic numbers. This extension, the splitting field extension, is Galois. It's normal and it's separable. It's normal because it's a splitting field extension. It's separable because Q has characteristic 0 and all extensions over such fields are separable. In particular, then, we know that the embeddings of S into A are the automorphisms of S. So we're bringing in a lot of powerful mathematics that we've been discussing. This set of automorphisms is a group under composition. This is not. The set of embeddings is not, unless the embeddings happen to be automorphisms, because you can't compose embeddings that don't map the domain to the same set. The codomain is the same as the domain. So this is critical to having a group under composition. Galois theory tells us that the properties of this group, which by the way is called the Galois group of the polynomial, reflect the properties of the extension, the splitting field extension, and conversely. Properties of this group tied closely to the properties of this extension. But it's, I think, generally felt that discovering the properties of groups is in some sense easier than discovering the properties of field extensions. I don't know whether this is really true or not. Is it fair to say group theory is simpler than field theory? Probably not. But maybe at some level it is. In any case, what the Galois theory tells us is that a Galois extension is solvable by radicals and therefore expressible by formula because of the results we've just been talking about, if and only if its Galois group is a solvable group. Now, I haven't discussed solvability of groups. We're going to do that at the appropriate time. It's a property of groups. But at least I'll give you the definition now, so it won't be completely in the dark. A group G is solvable, and in the European literature it tends to be called soluble, if it has a proper tower of subgroups where each group Gi is normal in the next group, and each quotient group is abelian. So, in this particular case, we're going to show that the Galois group of this particular polynomial here is the symmetric group S5. And we're going to show that's true because we're going to show it contains a transposition, complex conjugation, as well as a 5-cycle. And those two, we studied this in the group theory course, will generate all of S5. But it's a fact that the symmetric group Sn is solvable if and only if n is less than or equal to 4. So that should, a light bulb should go off. 4, 1 less than 5, where we start having trouble with formulas. So, the polynomial p of x is not solvable by radicals. Its Galois group is not solvable, and so its splitting field is not solvable by radicals, and so its splitting field is not expressible by formula. And so the roots of p of x, the generators of S, are not expressible by formula. This is very beautiful mathematics and quite deep. So because p of x is not, the roots are not expressible by formula, there can be no general formula for polynomials of degree 5. That's this degree. Okay? So in the next lecture, we're going to get more serious about our look at Galois theory.